Hello wonderful person, this is Anton, and in today's video we're going to be talking about pulsars. But specifically we're actually going to be discussing how pulsars work and what gives them these beautiful jets that we see emanating from two directions that once in a while hit Earth. Welcome to What the Math. So this right here are the two famous pulsars, Taylor and Hulse, that are actually real, and they're out there somewhere in the galaxy, sending their pulse waves toward Earth. And what's interesting about this particular simulation is that this is one of the few more or less realistic representations of pulsars. But the thing is, it doesn't actually explain anything. It doesn't explain how these pulsars get their jets and what is it that gives them these unusual projections. So in today's video, I'm going to just show you a little bit of the science behind it. And we're going to start with a few videos from NASA, starting with this one right here from NASA Goddard, and it kind of shows you how the actual pulsar may look like in real life, and the fact that it's actually extremely dense, extremely massive, and a single teaspoon of the material is equivalent to the whole mass of Mount Everest. Now, this is actual representation of a pulsar, and what you need to get from this particular picture is that a pulsar is a neutron star. Basically, it is just a neutron star. All neutron stars can become pulsars. More specifically, these lines are really important, and these are magnetic lines. It's a neutron star that is an extremely powerful magnet. So what makes neutron star is its extreme magnetism. It's basically the most powerful magnet you can imagine in the entire universe. Now, this is what happens when you see those jets passing in front of you, and this is what makes a pulsar. And I guess to simulate this a little bit better, we're going to use this online simulation, the link for which you can find in the description below. But basically, here is a neutron star whose magnetic axis aligns entirely with its rotation, so no matter how fast it spins, the jets always point in the same direction. But for most objects, including Earth, the magnetic axis is actually a little bit offset. So let's say it's offset by about 30 degrees. For Earth, it's not as dramatic, it's only a few degrees, but for a pulsar, it could be this much. And so here, the actual rotation is this way, this way, I guess. And the actual magnetic axis has to deal with the fact that now the actual object is spinning, and so the north and south of the magnetic field will actually be moving along with the rotation. Obviously, for pulsars, this is a lot faster. Most pulsars spin several times per second, and some of the fastest ones spin up to 700 times per second, but it would be really hard for us to imagine or to visualize this. Now, the reason we actually see things on Earth is because the actual inclination is also changed here, and so we're going to change this so that once in a while the actual ray is going to be hitting Earth, and you can see this is when we start seeing these pulses. And as the time passes, you will see that pretty much on regular intervals we'll get these pulses with slightly different energy. Now, this is why pulsars make some of the most accurate clocks in the universe, because this here can be measured extremely precisely. The actual time between pulses is extremely precise, more precise than even the most precise atomic clock. And so pulsars are incredible tools for that, for measuring time essentially. Now, one of the main reasons pulsars actually get so much energy, and one of the reasons why pulsars get these jets is, well, magnetism. It's really all about the fact that pulsars are the most powerful magnets in the world, and there's a really beautiful simulation from NASA that kind of explains to you why these jets only come from two directions. I'm going to show it to you right now. And right here, you can actually kind of see what's happening. So basically, the material that's around pulsar, the accretion disk around pulsar, is actually deposited in only two regions of space on the pulsar, in the north magnetic region and in the south magnetic region. Let me actually just zoom out of here a little bit again, just to show you this again. So the material that spins around the pulsar is moving in such a way that as it comes closer and closer, the magnetic field around pulsar forces it to be deposited only here and here. And this is because, once again, pulsars are incredibly powerful magnets. And this material comes from some kind of a companion next to the pulsar, so they will have to have something in the star system to actually have the accretion disk. If the neutron star doesn't have anything in the star system, it will not be a pulsar at all. It will just stay a powerful magnet, but all by itself. So let's just watch this again, and you can see that as the material rotates around the pulsar, it's deposited here, and as it falls on the surface, let's actually maybe advance this a little bit so you can see it. As it falls to the surface, the energy created through the collision is so ridiculously powerful that it basically starts emanating energy in visual light on radio waves, and all sorts of ridiculously powerful photons are being released, and those photons are what we actually see. So basically, this is the result of a collision between matter and the surface of a pulsar, and this produces two jets in two directions based on the fact that the actual magnetic field forces them to be deposited just there. Now, pulsars don't just emit this type of energy though. We've recently discovered that they also emit gamma rays. And gamma rays are the most powerful photons you can actually detect, basically the most powerful part of the energetic spectrum, and this is the gamma ray emission from a pulsar. So as you can see, it's actually not in the same region as the actual jets, and we've detected this from several globular clusters where we were able to see extremely powerful gamma rays coming off pulsars. There's still not an actual explanation for why we're seeing them, but as you can see, pulsars are actually a lot more complicated than meets the eye. So basically there's the actual energetic X-rays coming off these two directions, and even more energetic gamma rays coming off, I guess you could call it the side of the pulsar. And so why these are produced is another question, but we might be able to answer this in the future. And so in that sense, what this shows you is that these pulsars are basically ridiculously powerful magnets, and this magnetism produces the X-rays, it also produces the gamma rays, and in essence creates these very unusual star remnants that we on one side call neutron stars, but on the other side they also become pulsars if you give them any kind of matter in their star system. So if we were to throw away a few asteroids into these pulsars here, and those asteroids were to basically get absorbed by those pulsars, their emissions would actually increase in power, and we would be able to see even more pulsating events coming off the system. And so that's kind of the pulsars in a nutshell. So it's really all about the magnetism, and it's all about the fact that they're just extremely powerful, and they produce some of the most powerful radiation in the universe. Oh, and look at that, I just created something very unusual. I'm not sure what happened there, but it looked very, very beautiful, and it seems to have destroyed my whole system. Oh, okay, it created a star. Go figure. Not exactly what I expected to happen. Anyway, thank you so much for watching. Hopefully now you know a little bit more about pulsars, and you now know a little bit more about how the actual structure of a pulsar works and what produces these X-rays, and now you know that they also produce gamma rays, which are even more powerful than X-rays. Anyway, thank you for watching. Come back tomorrow to learn something else. I'll see you guys tomorrow. Space out, and as always, bye-bye. Oh, and by the way, if you would like to help this channel grow, do consider subscribing and potentially supporting this channel on Patreon, because it does help me produce higher quality videos. It's kind of time consuming, it's kind of hard, and you know, it takes a lot of time for one person to make all of this. Anyway, thank you for your support. Bye-bye.